Okay guys, this is the part 1 video for lesson 2.3 on higher degree polynomial functions with modeling. We have 5 objectives. We're going to graph higher degree polynomial functions, write the end behavior of a polynomial function as a limit, find the zeros of a polynomial function, learn about the intermediate value theorem, and solve modeling problems involving higher degree polynomial functions. In the previous sections, we have focused on polynomials of 0, 1, and 2 degrees. These were our constant functions, linear functions, and quadratic functions. Now we turn our attention to polynomials of degree 3, which are cubic functions, and polynomials of degree 4, which are quartic functions. Okay. I put a little bit of review of polynomial functions in the vocabulary here because it is very important that we're going to be dealing a lot, and we're going to be looking a lot at the leading term of our polynomials, our polynomial functions, in order to determine things such as end behavior, shape, maximum number of roots, and local extrema, and all that good stuff, which we'll get to here in a few minutes. So it's important that we know and we're solid with the vocabulary. Quickly filling in this guided note here at the end, so you want to remember also that the constant term is not only the initial value, but also the y-intercept. Alright, and then let's look down here at this polynomial function. Our a sub n, that's our leading coefficient. What is our leading coefficient here? Well, we look, and this polynomial is written in standard form. That means that the degrees are written in decreasing order here. So we're good, it's in standard form. The very first term is the leading term. The leading coefficient is just going to be 3 then. The degree, my n, the degree of this polynomial function is going to be 3. That's the exponent of my leading term, and then my constant is going to be -9. That's this thing hanging off at the end with no variable. Okay, let's do some examples now. We want to describe how to transform the graph of an appropriate monomial function f of x equaling a sub n times x to the nth power into the graph of the given function. Sketch the transformed graph by hand and support your answer with your graphing calculator. Compute the location and the y-intercept as a check on the transformed graph. So f of x equals a sub n times x to the nth power. This right here, if you look back at our definition, here is the leading term of our polynomial function. So what's the leading term of our polynomial function here? Well, in order to determine that, we'd have to expand that. And we're just looking at we're interested in the leading term, so this really is just looking at this so you guys kind of understand how I'm going to be getting the leading term. I'm going to expand out this x plus 1 cubed, and again I'm just focused on the leading term, so x times x is going to give me x squared, and I'm going to get a bunch of stuff after this. And then I'm going to have some quadratic multiplied by x plus 1. So this times this, that's going to give me x cubed. And then take this x cubed and multiply it by 4. So my leading term is going to be f of x equaling 4x cubed. Now, what type of transformations take me from this function to this function? And we have to write that down. I'm adding 1 to the x, so when we add to the x, go left. So this is going to be a horizontal translation 1 unit left. Alright, we now want to sketch the transformed graph by hand. Alright, so let me clear some room. Let me get rid of this. Alright, so our f of x, that was 4x cubed. Let's graph that. So it's going to look something like this. And then we want to shift this 1 unit to the left. So this was f of x. This is my transformed graph g of x. The last thing we want to do is compute the location of the y-intercept for g of x. So to find the y-intercept, substitute 0 in for x. So g of 0 is going to equal 4 times 0 plus 1 cubed. So g of 0 is going to equal 1 cubed is 1 times 4 is 4. So my y-intercept is 0, 4. So that's going to be that point right there. Alright, in the next example, h of x equals negative 1 times the quantity x minus 2 to the 4th plus 5. Alright, we want to compare this graph with f of x equaling negative x to the 4th. That's my leading coefficient of h of x. So when you expand this, your leading coefficient is going to be x to the 4th. Multiply it then by negative 1. And that's where I get negative x to the 4th. Alright, so what transformations take me from this to this? Well, I'm subtracting 2 from the x, so when I subtract 2 from the x, I have to horizontally translate 2 units right. So horizontal translation 2 units right, and then I'm adding 5 to the y, so that's a vertical translation 5 units up. Let's graph this. Alright, there's a rough sketch of negative x to the 4th. I'm going to take this vertex and move it 2 units right, and then 5 units up. I'm going to go by 2's on the y-axis. So over 2, up 5. That puts me there. And then let's compute the y-intercept so it's accurate. So let's do h of 0 equaling negative x minus, let's plug that stuff in. So 0 minus 2 to the 4th plus 5. So negative 0 minus 2 is negative 2. Negative 2 raised to the 4th is 16 times negative 1, so I have negative 16 plus 5. So I get negative 11. So my y-intercept is 0, negative 11. Again, I'm going by 2's. 2, 4, 6, 8, 10, 12. There's negative 11. Do one of that. Do one of that. Try and even it out because it looks crappy. You get the idea. Alright, so there's my rough sketch. You want to check using your graphing calculators. Go right ahead and do that. Okay, so now here we have typical graphs of cubic functions. Alright, and so we're going to look at two different scenarios. A cubic function when the leading coefficient is positive, and a cubic function when the leading coefficient is negative. So an example would be x to the third, or 2x to the third. Example here, negative 3x to the third. Alright? And what I want you to notice, I want you to look at what goes on with the end behavior when our leading coefficient is positive for a cubic function. Notice that when my leading coefficient is positive, the graph starts down and ends up. Okay, so as x goes to negative infinity, my graph f of x goes to negative infinity. And as x goes to positive infinity, my graph f of x goes to positive infinity. Alright, so a positive leading coefficient on a cubic function, the graph always starts down and ends up. And you can see the same thing happens here. I start down, end up. Now, if the leading coefficient, alright, of a cubic function is negative, right, I'm going to start up and end down. Okay? You think about this as doing the Elvis. Right? One finger points up, one finger points down. Or some dude doing a bad disco dance. Alright, however you want to remember it, but the end behaviors are the opposites of each other for cubic functions. Now, for quartic functions, alright, when the leading coefficient is positive, notice how the end behaviors are the same. Alright, so a positive leading coefficient, we start up and end up. Alright, and then if the leading coefficient is negative, it's the opposite. You start down and you end down. Alright. Okay. So what you will notice is that the end behavior of a function is closely related to the end behavior of its leading term. Okay, so for any odd degree polynomial function, this same pattern happens. So if I look back, it's not only so a cubic polynomial is an odd polynomial, and so for any odd, so this could be x to the 7th, x to the 9th, any type of odd polynomial function, the end behavior is going to be the same. So when you have a positive leading coefficient, you're going to start down and you're going to end up. When the leading coefficient of that odd degree polynomial is negative, you're going to start up and end down. And so what I want to do here is write the end behavior in terms of a limit. So how would we write this here? So we would say that the limit of f of x as x goes to negative infinity, so as we're going to negative infinity, where's the graph going? Well, the graph is going to negative infinity as well. And then here, as x goes to positive infinity, so the limit of f of x as x goes to pen's crapping out. As x goes to positive infinity, my graph goes to positive infinity. Alright, here the limit of f of x as x goes to negative infinity equals positive infinity. So I'm going towards negative infinity, but my graph is going up. And as x goes to positive infinity, so the limit of f of x as x goes to positive infinity equals negative infinity. Okay, so again, odd degrees, opposite end behaviors. Now, for the cortex, okay, what did we see? We saw that the end behavior, if it started up and ended up, if it started down and ended down, so the end behaviors were the same. Well, that is the same for any even polynomial function. So x to the 6th, x to the 8th, anything like that, you're going to have this pattern, the same pattern of end behavior. So let's write the end behavior here as the limit of f of x as x goes to negative infinity, that equals positive infinity. So towards negative infinity, as x goes to negative infinity, graph of f of x is going up. And then here, the limit of f of x as x goes to positive infinity, that equals infinity. Alright, and you guys can do this last one and fill that one in on your own. Alright, now I want to go back to these two graphs of quartic and cubic functions and get us to observe another pattern. Right, and that has to do with the number of roots of a cubic function. Alright, so again, cubic function, say y equals x cubed. I don't know. Alright, so let's see, how do we want to do this? Let's draw in a x-axis. Okay, and so I'm drawing in an x-axis in which it'll essentially intersect the graph in as many points as possible. Notice how I would have a root here, here, and here. So at the most for this graph here I would have 3 roots. Well, that corresponds with my degree being 3. Over here, even though my leading coefficient is negative, I would have here at most 3 roots. Again, corresponding to the degree of the polynomial. Now, how does the degree or the roots relate to the local extrema? Well, here I have a local maximum, here I have a local minimum. So I have at most 3 roots, and that gives me at most 2 local extrema. Same thing here. I have at most 3 roots, but notice I have a local minimum, here's a local maximum, so I have 2. So this, we will see if this will hold true. Will this pattern hold true with the quartic functions? So let's erase. Draw on an x-axis that intersects the graph as many points as possible. So 1 root, 2 root, 3 root, 4 root. So quartic functions. So raised to the 4th power. Alright. So 4th power, at most 4 roots. Same thing over here, even though my leading coefficient is negative, I still get at most 4 roots. Now, the local extremes, notice I have 3. 2 local minimums and a local max. Here, 2 local max and a local min. Alright, so how did I write it back here? At most 3 roots. So here, at most 4 roots gives you at most 3 local extrema, which leads us into this theorem. A polynomial function of degree n has at most n minus 1 local extrema and at most n zeros. Alright, so hopefully by doing those examples the theorem is clear. Alright, so let's do example 2. It says to graph the polynomial on a window showing its extrema and zeros and its end behavior. Describe the end behavior using limits. So we don't even need to graph this. Let's just look at what the leading coefficient is. So to do that, so there's my leading term. So my leading coefficient is A, and is that positive or negative? That's positive. Alright, now what's the other thing that I need to check? The degree. My degree is 3, so that is odd. So odd functions either start down and end up, or start up and end down. Well, since my leading coefficient is positive, it's going to be something like this, where I start down and end up. So we can write this as the limit of f of x. So as x goes to negative infinity, what's my graph going? Where's my graph going? That's going to negative infinity as well. And then as x goes to positive infinity, so the limit of f of x as x goes to positive infinity, so as x goes to positive infinity, my graph also goes to positive infinity. Alright, next one. Right, my A, or my leading coefficient, is positive again. My degree is 4, so that's even. So an even degree with a positive leading coefficient I don't know if that's what I'm gonna get something that looks like this. The bottom line is I'm gonna have something that starts up and ends up. Alright, so let's write these end behaviors as a limit. So the limit of f of x as x goes to negative infinity equals infinity. So as x goes to negative infinity, the graph goes towards infinity. As x goes to positive infinity, my graph goes to infinity. So the limit of f of x as x goes to infinity equals positive infinity. Alright. How many more? Last one, guys. Alright. And this is easy because we've done this. Find the zeros of the polynomial function here. Alright, so we have f of x equaling all of this. So let's factor out an x. Alright, so we're finding the solutions here. So f of x equals x times x to the second power minus x minus 6. Alright, and so when we're finding the zeros, we set f of x equal to 0. So 0 is going to equal x times, now let's factor this quadratic. So my signs, negative, negative, are going to give me a negative plus. I want factors of negative 6 with a sum of negative 1. So 3 and 2 here. Alright, so now you set all these factors equal to 0, so x equals 0, x minus 3 equals 0, and x plus 2 equals 0. So x can be equal to either 0, 3, or negative 2. Alright, so again, a video a little bit on the long side. Hopefully you stayed awake, hopefully you stayed focused. Go watch the Tribe. Hopefully you can get this win today, and we'll see you guys in class tomorrow.